In this lesson, we're going to learn about reaction stoichiometry and see how it applies to acids and bases. One of the things that happens a lot in acid-base chemistry is that very frequently there's a need to completely neutralize both the acid and the base. Remember, these two react with each other. So if you combine them in a place or in a vessel, they'll react with each other. And one of the great things about that, at least in chemistry terms, is that we can make some calculations happen to know how much of each substance was used. This is actually an old concept, but I want to bring it up again, is this phrase stoichiometric amount. This is the quantity, or these are the quantities of the reactants that result in the complete consumption of both reactants. If you remember, that means there's no excess reagent, nothing is left over. Also, there's not technically a limiting reagent either, because nothing is necessarily, air quoting here, limiting the reaction, because it all reacts with each other. Nothing is left over in the end. And of course, this is old news, but if we're talking about stoichiometry, that means we're relying on the mole ratio of a balanced chemical equation and applying this idea of how solutions work. So how exactly do solutions fit in? Let's go ahead and break this one down first. This one involves the solutions of nitric acid and barium hydroxide, and those are going to form barium nitrate, the salt, and water. Remember, this is a neutralization reaction, so we expect those two products, salt and a water, anyway, or no, back up. Water and a salt. So in this case, the salt is barium nitrate. Anyway, you have 0.300 moles of nitric acid provided to you. How many moles of barium hydroxide are needed to neutralize the acid? Okay, so I'm given 0.300 moles of the acid. And then I'm being asked about the mole amount of barium hydroxide. Well, what do you know? You actually can do that fairly quickly because you have a balanced chemical equation to know that for every 2 moles of HNO3, you will also need 1 mole of barium hydroxide to react with it. So hopefully you can see the math on this one. It's pretty straightforward. It's going to be 0.150 moles of barium hydroxide. Now, to make sure we understand what's going on here, right, we can always just put some numbers in to these conversion bridges and then just put some mole fractions, or mole ratios anyway, to convert between all of them. But what exactly does this mean? It means that this is the mole amount of barium hydroxide needed to completely neutralize and react with the given amount of 0.300 moles of nitric acid. So, in the follow-up question here, what are the stoichiometric amounts for this example problem? The stoichiometric amounts are the combination of 0.300 moles of nitric acid and 0.150 moles of barium hydroxide. Stoichiometric amounts. So those two amounts right there will completely neutralize each other, and there will be nothing left of either acid or base. Now, that's also not to say that nothing exists anymore. It's just that you formed new products, and that's going to be barium nitrate, which will have a lot of production of, and then some water too, because these two substances have reacted. In example number 2, we're going to change it up just a little bit. Notice how it's still the same reaction equation. It's still nitric acid. You still have barium hydroxide with the same two products in an acid-base neutralization. On top of that, though, you're given 0.300 moles of nitric acid, once again, that requires neutralization. So we want to go ahead and neutralize all of the given 0.300 moles of nitric acid. If you have 0.250 molar barium hydroxide solution available, how many milliliters of the base solution are necessary to completely neutralize the nitric acid? So if you notice here, right, we're talking about molar. So molar is a concentration. So there is, again, some container of this the barium hydroxide. This container has a certain concentration. Now, remember, right, we're talking about trying to completely neutralize it. So what we need to do is figure out how many moles of barium hydroxide would be needed to completely neutralize 0.300 moles of nitric acid. Well, if you remember the previous slide, the previous example basically asked us that question to start with. So first, we got to figure out, okay, with 0.300 moles of nitric acid, that's going to take 0.150 moles of barium hydroxide, right? Again, I just pulled that number from the previous page, but also know that that number is relevant here because they're asking the same thing to start. How many moles of barium hydroxide are needed to react with all of that? Well, it turns out it's 0.150. But again, that's not what the question is asking for. The question is asking us for a solution of this base. How much specifically in milliliters? So this is a mole amount. That's obviously not a volume amount. However, we're given some information about that can help relate us our mole amount and the volume, which ends up being this 0.250 molar barium hydroxide. So how's that work? Remember that the concentration is always a ratio of the mole amount that's given, or the mole amount of the solute anyway, so mole amount of barium hydroxide, and that's divided by the volume of whatever solution you're working with. Okay, well, what do we have? We have the concentration of a solution, right? The solution we can have as much or as little of as we want. We also have a mole amount of barium hydroxide, which we got from this step. And then we also are trying to solve for the volume of solution. So let's go ahead and make this work. Let's do some rearranging. To solve for this, I want to start off by doing 0.250 molar. That's equal to 0.150 moles. Solve for the solve for the volume of solution. Do some quick geometry, and by geometry I mean algebra. And then your volume of solution ends up being 0.600 liters. And you got to be careful about your significant figures here to make sure you include those zeros at the end. Now, of course, finally, that's not really the question it's asking us for. It's asking us for a volume, but specifically in milliliters now, so let's make the conversion happen. To finish it out, 0.600 liters of solution. You have for every 1 liter, 1,000 liters, so that milliliters, excuse me. So that means it'll give you 600 milliliters. That's going to be your final answer. So to kind of review the problem, right, we're given some mole amount of nitric acid, right? We don't exactly know how it's presented to us, but we know that there's some nitric acid involved. And then you're also given some barium hydroxide as a solution. So you're basically taking a container here. Right now you got some HNO3 in there. And then in a separate container, you have some base, right? In this case, it's going to be a concentration or solution of barium hydroxide. And basically the question is exactly how much of this barium hydroxide is needed to be added into this so that they completely neutralize. And based on this work, we figured out that it's going to be 600 milliliters of this solution needed to cancel off or neutralize all this HNO3. Notice how we're talking about a volume as a solution. So a lot of this is actually just going to be water, right? That's the medium that you're dissolving the barium hydroxide in. And the only parts that actually react, of course, is the barium hydroxide with the nitric acid. All right. Here's the last one. A beaker contains 300 milliliters. By the way, this is the exact same reaction equation as before. A beaker contains 300 milliliters of a 0.500 molar solution of barium hydroxide. How many milliliters of that solution of nitric acid are necessary to react with the base? Okay, so let's go and take a look. First of all, we are this time given information about barium hydroxide. And then we're given a solution of some volume. I don't know exactly how much we need, but we do have some ability to use 0.250 molar nitric acid to then completely react with that given amount of base. So if you're kind of connecting what we've done already to what we have to do here, remember the key is that we need to use the mole ratio somehow, some way to help us figure out how much of each substance is around. Unfortunately, though, we're not given a mole amount quite like we were in the previous ones. We're not just given 0.300 moles of something. We're given that information in sort of a roundabout way. What do they tell us? They give us a volume of the base solution. They give us the concentration of the base solution. If I'm given a volume and a concentration and molarity of any solution, I can then figure out how many moles of barium hydroxide, and how many moles of barium hydroxide are involved. Let's see how that might look. All right, remember that we have 300 milliliters. Of course, we can't just use 300 milliliters as is. All the work in molarity involves the use of liters. So let's make that conversion happen real quick. That'd be 0.300 liters. Then, knowing that my concentration of barium hydroxide is equal to 0.500 molar, I can then set that equal to know that I'm solving for the mole amount of barium hydroxide, knowing that I have a volume of 0.300 liters. So basically what I just did there in the previous step, that can go ahead and plug in right there. Do some quick rearranging, and then I figure out that the mole amount of barium hydroxide is equal to, is equal to 0.0150 moles. Just kidding, that's 0.150 moles of this base. Now, that's about the base, right? That's what the information is given to me about the base. I'm not actually being asked about the base. I'm asking about the corresponding, I've been asked about the corresponding amount of nitric acid. So let's get the corresponding amount of nitric acid that be involved. Since I know that 0.150 moles of barium hydroxide is involved in this reaction, and I know that I have a mole ratio that helps me relate them, I can go ahead and set up a conversion bridge using the mole ratios to get what I need. You know what, just for the sake of having some colors here, let's go and use red to represent the acids. That's every 2 moles of HNO3, just like that. Do some math here, and you get 0.300 liters. Just kidding, 0.300 moles of HNO3. Now again, the key thing about this specific calculation is that this is the mole amount of HNO3 that will completely react with the 0.150 moles of barium hydroxide you figured out from using this solution. All right, this solution right here tells you that. Now, let's go ahead and finish it up. Since I know I have 0.30 moles of HNO3, I'm going to try to address the question. The question is asking me about the volume of another solution. So I'm going to have a concentration. I have to get the volume. I'm given a mole amount. Let's go and apply that molarity formula again. So the concentration of HNO3 is given to me as 0.250 molar. And I know that's going to be a ratio between the 0.300 moles of HNO3 that I calculated from the previous step. That's how many moles of HNO3 I need to react. But how do I get that? I don't know. I have to solve it by putting in a volume of the acid solution in. So that's my question mark. I don't know that. Do some quick rearranging. And I find out that the volume of the acid solution, represented here in red, that's going to be equal to 1.20 liters of solution. So I needed to take this 300 milliliters of barium hydroxide and combine it with 1.20 liters of the nitric acid so that everything will react with each other and you have no longer any acid or base left over. Now, to finish out the problem, of course, you've got to make sure we answer the right thing. It's asking for milliliters. So to convert this, 1.20 liters, let's go ahead and make this happen. Don't forget that significant figures are going to be important, so when you do this, you'll find that the only way to represent this accurately is by doing this bit. Let's try that again. I do not know how to write. 1.20 times 10 to the third milliliters. We cannot leave this in decimal form. All right, so that about does it. So whenever you see these problems, make sure you know that you're going to have to involve some stoichiometry. But before we can stick things directly into a simple stoichiometry problem like these right here, you might have to do a little work like doing some mole to liter conversion or molar to liter conversions using this molarity formula, or even doing some milliliters and liter work as well. All right, that'll do it.